Welcome to The Explainer. Today we're taking abstract physics and turning it into a fun, everyday classroom lesson to uncover exactly why the objects around us bend, stretch, and, well, sometimes completely break. Have you ever wondered why a rubber band just magically snaps back into place? Or why a paperclip permanently bends when you're fidgeting with it? Or maybe how massive steel bridges can possibly hold thousands of cars without just collapsing into the river below? If so, you are in the exact right place. Let's jump right in.
Here's our quick syllabus for the day. We're going to start by busting the myth of rigid solids, then we'll map out the vocabulary of stress, strain, and stretch. After that, we'll explore bending, breaking, and plasticity, and finally, we'll wrap up with how engineers use all of this to build safe bridges and structures.
Okay, Section 1, the myth of rigid solids. Let's go ahead and shatter a really common illusion right out of the gate. Absolutely nothing in our physical world is perfectly rigid. No matter how solid something looks, I promise you, it can be changed.
Think about a common steel spring versus a block of putty. When you pull on that spring, it stretches out, right? But the absolute second you let go, it snaps right back into its original shape like nothing ever happened. Now, take that putty. If you squish it with a heavy downward force, it just turns into a flat pancake forever. There's no snapping back. It literally just accepts its new reality.
So here's the crucial, unbreakable rule for our lesson today. Elasticity means a temporary shape change. Plasticity means a permanent deformation. And understanding the difference between these two states isn't just some abstract idea you memorize for a test. It's the absolute bedrock of all safe engineering design on Earth.
Moving right along to Section 2, stress, strain, and stretch. Let's step up to the chalkboard and define the exact scientific vocabulary we need to figure out how these invisible deformations actually happen in the real world.
In physics, we really have to distinguish between these two vital terms. Stress is the internal force acting over a specific area that causes the change. Think of stress as the root cause. Strain, on the other hand, is the actual physical stretch or squish in the material itself. Think of strain as the effect. So, stress happens deep inside the material, while strain is the physical change you can actually see with your own eyes.
Imagine pulling straight up on a metal cylinder. That pulling force spread across the top area, that's your stress. Because of that applied stress, the cylinder physically elongates. That change in length, when you compare it to its original resting size, is the strain. It's really just a simple chain reaction. Stress causes strain. Now, for small deformations, we follow the golden rule of this branch of physics, which is Hooke's law. This law states that stress and strain are perfectly mathematically proportional to each other. Basically, if you double the weight on a spring, meaning you double the stress, you're going to get exactly double the stretch, which is the strain. It makes this beautiful, perfectly predictable straight line on a graph. But, and this is a big but, this perfect harmony only holds up to a very specific critical limit.
Which brings us to Section 3, bending, breaking, and plasticity. So what exactly happens to a solid when we push way past that safe, proportional elastic limit and actually cause permanent damage? Let's find out.
Imagine mapping out a material's traumatic journey under immense pressure. It starts off totally fine, just a safe temporary stretch. But once it passes its elastic limit, it crosses a point of no return. This is the plastic deformation region, where the material gets a permanent set. If you relentlessly keep adding stress, it eventually hits its absolute ultimate tensile strength right before hitting the fracture point. And that is where total structural failure happens. Snap.
And this concept is incredibly relevant to the stuff sitting right on your desk. Think about nervously bending a paperclip back and forth. You are literally experiencing ductility in real time, right in that long plastic region. The metal permanently bends, but it takes quite a bit of effort to finally break it. Contrast that with, say, dropping a drinking glass on the kitchen floor. Glass perfectly demonstrates a brittle material. It has almost zero plastic region. It hits its limit and just shatters instantly, without any warning at all.
But hang on, I want you to pause and really think for a second here. Do all everyday items actually play by Hooke's perfectly straight, proportional rules? The fascinating answer is no. No way. We have these amazing exceptions called elastomers. Think of a simple rubber band, or even crazier, the elastic tissue of your own heart. These materials have absolutely vast elastic regions. You can pull them to several times their original length, and they still naturally snap right back. But the crazy part? They completely ignore Hooke's law. They stretch wildly, totally refusing to follow a mathematically proportional straight line. All right, Let's wrap this up in Section 4, Building Safe Bridges and Structures. Let's take all these classroom concepts, the rules of elasticity, the breaking points, and see how clever engineers apply them to build the towering, safe structures we drive over every single day.
Engineers actually quantify a solid's resistance to length change using a brilliant metric called Young's modulus. Think about testing different materials, like aluminum, copper, and steel, under incredibly heavy loads. When you apply the exact same massive downward force to all three, the aluminum stretches quite a bit, the copper stretches a little bit less, and the steel barely budges at all.
Now, this brings up a really wonderfully counterintuitive fact in physics. You might casually think, oh, a rubber band is highly elastic because it's so easy to stretch. But in the world of physics, requiring more force to stretch actually makes a material more elastic. Why? Because it vigorously resists deformation and fights tooth and nail to keep its original shape. For perspective, steel requires a massive 2,000 newtons of force just to stretch by a mere 0.1%. That incredible rigidity is exactly why steel is the undisputed king of heavy-duty structures.
So engineers know steel is remarkably strong, right? But it's also incredibly heavy and super expensive. To solve this, they shaped that steel into I-beams. It's honestly a genius design. By running the math on bending stress, they realized that they could prevent sagging way more effectively by making a beam deeper rather than just wider. That iconic I shape maximizes depth to stop the sag, gives a nice flat top for the load, and entirely hollows out the dead weight in the center. It saves a massive amount of money and raw material without sacrificing an ounce of safety.
We also see this deep understanding of strain in other everyday things. Look at braided crane cables. A solid steel rod thick enough to lift 10 tons would be ridiculously stiff and impossible to bend over a pulley. So engineers braid multiple thin wires together instead. It's a perfect combo of strength and spooling flexibility. Or think about pillars with those dramatically flared ends. Instead of a simple flat column that might crack under the immense weight of a building, flaring the ends distributes all that compressive stress over a much larger area, keeping our tallest skyscrapers safely upright.
And just to blow your mind a little as we conclude our lesson, these exact same mechanical principles don't just apply to paperclips and bridges, they apply on a massive planetary scale. This is literally why mountains can't just keep growing indefinitely into space. The base of a giant mountain experiences overwhelming shearing stress. Eventually, the sheer downward force of all that stacked rock exceeds the rock's critical elastic limit. Earth's own gravity literally forces the bedrock at the bottom to yield and flow outward like putty. This acts as a mechanical cap, limiting the maximum possible height of any mountain on Earth to about 10 kilometers.
So, as we wrap up this explainer, I want to leave you with this final thought. The next time you're stretching a rubber band, nervously bending a paperclip at your desk, or driving your car over a massive steel bridge, take a second and consider this. What other invisible limits of stress and strain are quietly holding the objects in your life together or subtly pushing them right to their breaking point? Keep observing, keep learning, and I'll catch you in the next explainer.